right, good morning. Okay, today we're going to look at 15.7. And I hope you had fun with double integrals, because today we're going to do triple integrals. And actually for the next few days. All right, so first of all, let's go back to a double integral here for just a moment and look at the meaning of what the double integral was telling us. Suppose we're integrating some function f of xy over a region D. And this region looks something like that. So what we're doing here is that we're accumulating this function f of xy all over that region. On each small differential element, dA, that's dx dy or dy dx, right? So remember that what we're really doing here is a Riemann sum of a bunch of tiny, tiny rectangles. We're integrating over a small rectangle with some kind of function. You could interpret that as a height, and we move it all over the region. When you do a triple integral, 3 integration, and we'll call this region B here. What you're doing is integrating a function of 3 variables, f of x, y, and z. And when you integrate in 3 dimensions, you're not dealing with a differential element of area anymore. You're dealing with a differential element of volume. In one variable, it's a small differential element of a length of a small line. Here you have an area, and here you have a volume. When you go to 4 dimensions, you have some kind of 4-dimensional volume. We can't picture that. We can't even interpret what that means easily, but mathematically, it's identical. So imagine you got this B, that's some kind of object here. What we're doing here is we're taking one tiny little rectangular solid out of this thing. This would be dy, dx, and dz. It doesn't have to be a cube, but once you shrink these things, eventually it looks more or less like a cube, but it's some kind of rectangular solid. The interpretation is the same. You're just accumulating this function on each of these tiny little cubes all over that solid. On each differential element dv all over that solid that I called B. And this is also a Riemann sum. It's that little area, that volume multiplied by whatever the function is at that point. And if you're doing a Riemann sum with this, now you have a bunch of different potential sample points you could use. You could use any of these 8 corners or any of these midpoints. There are lots of different choices to use as a sample point for Riemann sum. We're not going to look at the Riemann sum for that, but it gets messy, and it's very similar to the double integral. Now mechanically, you handle a triple integral just like how you handle a double integral. So for example, if you have this integral right here, you treat it exactly the same thing as if it's a double integral. You integrate inside out, right? So this would be 0, 1, 0 to z. X dx is 1/2 x squared. And now you got 3 variables to track. So you really got to be careful what you're substituting in for what. With two double integral, you can probably keep track of it, but as the number of variables grow, keeping track of these things is going to be increasingly difficult. Okay, so anyway, we end up getting this thing. Then now you got a double integral. We know what to do from here. 0, 1, and that's a 1 over 6 y cubed. Y is equal to 0, y is equal to z. That's a z, sorry. dz last. So what's this thing? 0, 1, 1 over 6, z cubed dz. And this becomes easy to do from here. 1 over 24, z to the 4th. Only got one variable left. I don't have to track what it is. So 1 over 24. Okay, I did that very quickly because you know how to do it. Mechanically, it's identical to a single, double, and basically however many integrals you're doing, it's exactly the same process. Integrate inside out. Setting up a triple integral is just like setting up a double integral, except it gets a little bit more complicated. Just a little bit. By about 50%. Right? From 2 to 3. Anyway. Okay, let's find out this thing right here. Triple integral over some volume, we'll call that E, of x dv. Where E is the solid under the plane x plus 2y plus 3z is equal to 6 in the first octant. Okay? Okay, so let's make a rough sketch of this solid that we're dealing with. Last time you saw how you could sketch this pretty easily. Basically, you make 2 of these variables 0, 1 at a time, 2 at a time, and then you can find out the intersect. So if y and z are 0, x is equal to 6. So this thing will intersect the x-axis at 6. If x and z are 0, then y has to be 3. So y-intercept is 3. If x and y are 0, then z is 2. Z-intercept, therefore, is 2. So you have this plane that slices through the coordinate system diagonally. We're interested in just that portion in the first octant, where all 3 variables are positive. Okay? So the setup is very much like double. Let's first take this region on the xy plane. Take a look at it. On the xy plane, we see a triangle. Goes from y is equal to 3 to x is equal to 6. And this equation is y is equal to 3 minus 1 over 2x, right? Okay, so you take one of these projections. If you don't know which one to take the x and y plane. And then you start just by, as if you're setting up a double integral looking at this region D. Okay, so if I'm looking at this region here, the simple thing to do here is to say x is between 0 and 6, right? And then y is between 0 and 3 minus 1 half x. So that part is just like a double. You see a region, you make one of these things constant bounded, you make the other one a slightly more complicated one. We could have chosen y to go from 0 to 3 and then x to be something involving y, right? Either of those is fine. So this would describe the region D here. And above D, there is a height defined by that plane right here. So if I know, this describes everything in D. Every single point in D can be described this way. For each point, there is a z height seen here. That's a function of x and y. So I can look at this equation here and solve for z. And we get z is equal to 2 minus 1 over 3x minus 2 over 3y. And that's the height of that plane. Okay? And z is bounded above by that plane and bounded below by the xy plane. So this bounds above, z equal to 0, bounds below. Because we're only interested in the first octant, we don't go below xy plane. So now this will tell me that z is going to go from 0 to 2 minus 1/3 x minus 2 over 3 y. All right, does that make sense? Yes? Okay, now when you put this all together into a triple integral, same rule as usual. The one that's bounded by constant goes last. So x has to happen very, very last. Then you go in order of complexity. Once we know x, y is described. So y will go next. And then z, notice z depends on x and y. So this has to be integrated first. And I'll write all that down. Okay, so the variable with constant bounds has to happen last. The variable with the most complicated bounds Often that's the bounds that it contains the most number of variables. So x doesn't contain any variable. Y contains one variable. Z contains two variables. And this one's going to have to happen first. And then the remaining one, of course, is going to happen in the middle. So for this one right here, the way we set this up, we're going to have to go Z first, Y next, and X very, very last. But when we write it, remember, the last one is the outside one. So the very last integration is 0 to 6 for X. This is our X bound. And then next one is the Y. Y goes from 0 to 3 minus 1/2 X. And last, or first actually, we write it last, but we actually perform that integration first. 2 minus 1/3 X minus 2/3 Y. And that's the Z bound, right? Again, Z contains the most complicated bounds. It has the most number of variables. And what are we integrating? We're integrating X. And dV is going to be dz, dy, dx. Okay, so that's the integral that we will end up calculating. And you know how to do this, so I'm not actually going to work this out. You know how to do it. Any question on this particular integral we just set up? Good? Yes? Good. Now let's talk about order again. We have 3 variables. So how many different orders are there? 6? And how did you find that? Okay. Why 3 times 2 times 1? Yeah. So what you said is, yeah, absolutely. You have 3 choices for the first variable. Once you make that choice, you have 2 remaining choices for the second variable. And then you have one last, there's no choice for the last one. So you have 6. 3 times 2 times 1. So 3 is the ways to choose first. Once you've chosen that, you have 2 remaining choices to choose the next one. If you choose X to go first, then you have Y or Z to choose from for the second one. Once you made that choice, you got 1 remaining choice. So you got 6. In general, it's n factorial, where n is the number of variables. So a double integral is 2 factorial. There are 2 ways to do it. A triple is 6. A quadruple, if you ever encounter that kind of thing, has 24 different potential orders. Let's list the 6 different orders we get. 3 choices for the first one. So let's start with dx. I've made a choice for dx. Now I have 2 choices for the next one. I'll choose y, dy, dz. Right? And then let's stick with x as the first choice. I can do dz next, and then dy. Then I can do dy first. Now I can choose x or z to go next. I'll choose x first and then z last. I choose dy first, dz next, dx last. Right? You see how this is working out? You have three different ways to choose the first one. Each time you make that choice, you have two remaining ways to choose the next. dy, dz, dy, dx. So here are 6 different ways that we could do the integration. And we just did dz, dy, dx, this guy right here. Okay, let's choose one of these and do another example with the same solid. Let's go with, how about this first one? Let's try this one, dx, dy, dz. Okay, same region, same solid E, same integration we're doing here. E is the same as last time, under plane x plus 2y plus 3z is equal to 6 in first octant. And now we're going to go in the order we have chosen here. We're going to do x integration first, y next, and z last. In other words, we want dv to be equal to dx, dy, dz. Okay, we'll just redo everything we just did. Starting with our rough sketch of the, well, this is a pretty good sketch because it's a very simple shape. But in general, it will be a rough sketch. All right, now we're going to have to read this thing backwards because dz at the very end means z is integrated last. That means z is going to have the simplest bounds, the constant bounds. And looking at the picture here, it's pretty clear what z is going to be. Z is going to be bounded between the floor, which is xy, and the tip here, which is 2. Right? So z is going to take the simplest bound because z is happening, integration for z is happening at the very, very, very end. Next, we're going to do y. And the fact that it comes after z means that we want the relationship between y and z. We want y as a function of z, because z has already happened. Once I've chosen a z, I need to know how y is dependent on z. X has not even come into the picture yet, right? The way we read this thing here, if z is equal to 2, what is y? Once we know what y is, let's say 3, 2, 3, then what is x? That's the order that we're going to be looking at things. So what I want to do here is to look at how y and z are related in the yz plane. And this time, z has already been determined. You choose a number somewhere between 0 and 2. So I know what z is. So I'm going to put z on the horizontal axis. That's already known. And I want to know how y will depend on z once I have chosen a z. This is no different than what we did. First, we gave x a simple bound. And then we found out how y depends on x. And then we found out how z depends on x and y. Exactly the same thing. We're just starting from a different face of that. This, by the way, is called a tetrahedron. It's just a really fancy word for a pyramid. So we're just looking at a different face of that tetrahedron to start. All right, so looking at how z and y are related, look at the intercepts. Y has an intercept of 3, z has an intercept of 2. So this equation here is y is equal to 3 minus 3 over 2z. And looking at this region here, this is becoming our region D, just like last time. Y clearly is bounded between 0 and the ceiling in this picture, 3 minus 3 over 2z. All right, so lastly, above this thing or below this thing, it doesn't really matter. There's some kind of x height, right? We need to see how x is dependent upon y and z. Look at the plane equation here. If you solve for x, then you see x is 6 minus 2y minus 3z. And x is anywhere between 0 and whatever x goes out to. So this means that x is going to be between 0 and 6 minus 2y minus 3z. So far, so good? Good. Now this integral, now we can put this whole thing together. Simple bound happens last. We know that already. 0 to 2. Next is y. Y is between 0 and 3 minus 3 over 2z. And then finally, the first integration that we do, but it's actually the last bound that we determined. It's the most complicated one. 0, 6 minus 2y minus 3z. We're integrating x dv, and dv will be dx dy dz. Okay? Then once again, we're going to skip the calculation of that. It's not difficult, it's just annoying to do. Okay? Questions? And there are 4 left. You have 5 minutes to find all 4 of those. No, you don't. But, okay, you know how to do the rest of them, right? I show you 2 here, but if you take the time, you can come up with all 6 of them exactly the same way. You just choose a face to start, and then you do the rest of it. You have a homework problem where I think it's the very, very last one on WebAssign where they ask you to find all 6 different orders of integration. Have fun with that. But I just showed you how to do it, so you'll do fine. All right, let's try this example. Find the volume of a solid bounded by the cylinder x squared plus y squared is equal to 1, and the planes z is equal to y and z is equal to 0. You have a cylinder and you have a plane, 2 planes that slice through the cylinder. And bounded between those 2 planes, you have this wedge-shaped thing. That's the volume that we want to find. Okay, z is equal to 0 is xy plane. So that's the floor. And the cylinder, there's no z in here. So this is a bunch of circles with the radius 1 centered on the origin in the xy plane, going up in the z direction. So that kind of thing here. It's a circular cylinder. One plane is z equal to 0. That's just the xy plane that bounds below. And z is equal to y means that this plane will look like z is equal to y on the zy plane. There's no x in here, so it has infinite height in both x directions. So that plane is going to look like something like this. Okay? It's like when you buy one of those cookie dough thing you can get in the store. Open it out, it's a tube, and you make a diagonal cut. That's the kind of thing we're dealing with. So we end up dealing with this kind of shape. Here's my attempt to sketch it. How's that? Can you visualize what we're dealing with? It's a wedge out of this tube. Can you see it? Can you draw better? Good for you. Okay, so that's what we got here. All right. Once again, to set this up, you're just going to have to choose one of these planes to be the floor and start setting up simple bounds, next complicated one, then the very last one. For this one here, it looks like x and y plane is probably the best choice to work with. It's the most logical one. So let's start with that. And in general, when you're dealing with these things, if you don't know which ones to start, just start with the xy plane. If it's a very difficult one, then choose a different plane to start. On the x and y plane, the projection of this thing onto the xy plane looks like a semicircle. right? It's a tube that comes out of the page, and we're taking a slice of that diagonally. But the projection of that thing onto the xy plane is still going to be a semicircle. And x is going to go 1 here and minus 1. Okay? And y, this is the half of the circle in the positive y direction. So if I solve for y here and then take the positive root, that's going to describe the curve bounding above for y. And this part is just like setting up a double integral. We start with these two variables and let z be something else after we're done with x and y. And again, let's choose x to be simple bounded simply by two constants. That seems obvious. And y, once we know x, y is somewhere between 0 and radical 1 minus x squared. Right? So you've done that with a double integral. Not difficult to do. Next, once we've determined the region, the projection of the region we're looking at the z height now. On this semicircle, there's some kind of z height for each and every point. And if you look at this, z obviously can never go below the xy plane. So that's going to bound below. What about the upper bound? What do you think? Y, right? Notice the plane, because the way it slices, the height doesn't depend on x. It only depends on y. Y. And then the order here would be x on the outside, y in the middle, and z first. So we do z first, y next, and then x when we integrate. But notice that when we determine the bounds, we go in the reverse order. So the volume will be minus 1 to 1, 0 to 1 minus x squared, and then 0 to y. And what are we integrating when we want to find the volume? We integrate 1 times dv, and what would dv be? dz dy dx. Good. Okay, again, I'll skip the integration here. You know how to do it. It's a pretty simple one. Questions? Now, sometimes, remember, if you're dealing with a circular region, D, often it's more advantageous to go to polar. So let's see how we can do that kind of thing with this example. All right, so let's take the xy region back. Minus 1 to positive 1, minus 1, and that's also 1. And that's, of course, circle of radius 1, a portion of the circle of radius 1. Okay, so describe that region here in polar coordinates for me. What are the bounds of theta? 0 to 1 pi, right. And then? Zero to 1, yeah, because we want the entire semicircle. Okay? So you want to start accumulating everything. All the points that exist on D starts at here and moving way out once you've determined an angle. And now we're going to we've gone to polar. So remember that dx dy, that's our dA on that plane. In polar, what would that be? Right, r dr d theta. Okay, and we're going to let z remain as in the last example. There's no reason to adjust z. The only thing we need to adjust here is this y. And what's y in polar? R sine theta, very good. So therefore, when we do the integration here, here are the polar bounds. This is theta. This is r. And then z goes from 0 to r sine theta. Right? And dv used to be dz, dy, dx. But this part has turned into r dr d theta because we went to polar in the xy plane. So that part of dv turned into r dr d theta. So now we're integrating r dz dr d theta. And I brought this r out here. And this is the equivalent integral with the x and y plane described by polar coordinates. Okay? Questions? All right, let's do another one. Let's do another one where polar can help the integration. Let's find the triple integral over E of z dv, where E is bounded by z is equal to x squared plus y squared, and z is equal to 4. Okay? Let's see what we're dealing with. All right, what shape is this? Z is equal to x squared plus y squared. Paraboloid, very good. It's a circle in the xy plane, growing with z, and in the zx plane we have parabola. In the zy plane we have parabolas again. So it's a paraboloid, circular paraboloid. Z is equal to 4, that's obvious. It's a plane that cuts parallel to the xy plane that cuts off at z is equal to 4. So it's this paraboloid and with a cap on top of it. And we would like to integrate z dv. Okay, so again, start with a projection of this shape. You look at this thing here, if you're looking down onto the xy plane, what will you see? Obviously, you will see this cap at 4. So you're looking down here. On the xy plane, the shadow of this object is going to be a circle of what radius? Z is equal to 4, so the cap here is a circle, x squared plus y squared is equal to 4, so a circle of radius 2. Good. Okay, so that's our D region here. It's a circle, so polar seems like a very good choice to do that. And also seems really easy to describe this in polar. Right? Theta between 0 and 2 pi, the complete circle, and r goes from 0 to 2. We want the entire circle. In order to get every point in that circle, we have to look at these two bounds. All right, so what would the bounds of Z be? From r squared to 4. Okay. So notice just some little rectangle box inside that paraboloid. The height of that thing is bounded above by 4. So this thing right here, Z is equal to 4. And bounded below, this is by some part of that paraboloid, right? So this one is Z is equal to x squared plus y squared. Now remember, all we're doing is just a bunch of really, really tiny rectangles, rectangular bars. So the bound is, in Cartesian, of course, is x squared plus y squared to 4. But we've gone to polar here for x and y. In fact, x and y are gone, so we got to go polar here too. X squared plus y squared is equal to r squared. We know that. That's a polar conversion. So that's the polar one. So these will become the bounds of Z. All right? So theta 0 to 2 pi, r 0 to 2, and then Z, r squared to 4. What do you do with this Z? You leave it, yeah? You leave it. What about dV? R dz, dr d theta, right? dz, and then r dr d theta is equivalent to dx dy, or dy dx. So this is the integral that you would need to perform to get the this triple integral. All right? Okay, that's it for today. Have a good weekend. See you Monday.